Hello, welcome to video 17 in my lecture Advanced Mathematic Modeling. In the last videos I showed you the ways to calculate, characterize probability distributions by moments, and then we learned about the characteristic function for discrete probability distributions. And in this video I want to show you some of the fundamental examples, the most basic examples of discrete distributions, and show you how to calculate, how to apply these techniques. So we start with the Bernoulli distribution, and this was the example we had very often. That was the biased coin. Or a pin. This thing, when you throw it, can either land in this position or this position. And so we have a discrete binary event, 0 or 1. So this is our P to have event 0, or we have P equal of 1, probability of outcome 1, and this we call P, and this is then 1 minus P. Sometimes we call this here Q. Yeah, so we just have two outcomes. We have a binary distribution, and the distribution is characterized by this one parameter, P. And the biased coin, the normal coin, would be P1 over 2. So we can plot here the distribution. So of our random number, so we have two values. We can either have 0 or we can have 1. And here we have the value P, and here we have 1 minus P. So our distribution is characterized by these two numbers. So now, how can we characterize the distribution? Let's calculate our expectation values. What's the expectation? What's the average outcome when we throw a biased coin? So we have the event, the outcome 0 with the probability 1 minus P plus 1 with probability P. So this gives P, so that's the expectation value. Let's look for the higher moments. So we have 0 to power n times 1 minus P plus 1 to power n times P. And this gives again P. So in this simple example, all higher moments, and actually all moments, are just P. And then we can calculate the variance as the expectation value of x squared minus x expectation value squared. So this is P minus P squared, or P times 1 minus P. So that's the variance of this distribution. And that's typically, with these numbers, the expectation and variance, that's typically enough for us to characterize the distribution. How would we have calculated these values with generating functions? Let's do this here. So when I do this, I hope this will not be too boring for you, but so I use, especially with choice, I use this very simple examples first to show you how the framework, how the method works, and later we will have more interesting distributions. So we need to calculate this generating function, and in the simple case here we just have two values, so our sum So in the sum we have only two terms. We have P0 times S to 0 plus P1 let's write it like this, P1 times S, and so we have Q, S to the power 0 is 1, and then we have here plus P1 is P times S. So this means the generating function in this case is a linear function which starts with Q equal 1 minus P, and approaches the value 1. Where is this 1? If you take S equal 1, then have you P plus Q is 1 minus P, so 1 minus P plus P equals 1. So the characteristic function is just a straight line. So let's see how can we generate all properties of our distribution from the generating function. So what's the f at position 0? That's just Q. So it's 1 minus P, and this is exactly what it should have been. So that's P0. What's the derivative? df over ds at position 0. That's just P. And this is exactly this P1. And if we take higher derivatives, df over ds at position s equals 0, this is 0. So we will find all other pi with I is larger than 1, or larger, yeah, write it like this. They're all 0. So we just have two values in the distribution. So you see, with the linear function, we just have two contributions here. And so if we would have just known this function, we would directly have seen the values of the distribution. So how can we calculate moments with the distribution? So we know the expectation value of x. That's just the derivative df over ds at s equal 1. So we take the derivative, it's just p at this position 1. So we just have p, and it's the same same thing we found here. So what is the x times x minus 1? That is the second derivative of our generating function at s equal 1. So now the second derivative of a linear function is 0. And then, so we know that the expectation of x squared minus expectation of x must be 0. And then we see that the second moment must also be p, what we have seen here, and then we can calculate the variance. So you see, with the generating function, we basically can obtain everything we had here. And if we do a straightforward calculation of moments, and in this example we do not really see the benefit of calculating first the generating function, but it's a simple example to show you how this is done. Let's go to something more interesting. Let's stay with the example of a Bernoulli trial, but now we don't make just a single Bernoulli trial, we make many of them, and we wait so long until we have success, until we have the event 1, until we have had. So we go from the Bernoulli distribution to the waiting time of many Bernoulli distributions. So assume now we have a series of independent Bernoulli trials, and we want to calculate this W, the waiting time for success. And success is that the outcome of the Bernoulli trial is 1. And so what is the probability that our waiting time equals k? This means we have to throw our coin exactly k times until we have the first time success. So we get this, that we have k minus 1 times we don't have success. So no success is the probability to have 0, so that's 1 minus p. And so we have k minus 1 throws that we have no success, and in the kth throw we have p. So the probability that we have a waiting time of exactly k is p times 1 minus p to k minus 1. So that's the probability distribution. P 1 minus p to k minus 1. And this is now a probability distribution of the random number k, where k can be 1, 2, 3, and so on. So if we look for waiting times in Bernoulli trials, we obtain a new distribution for k, and this distribution starts at the value 1. We can plot this distribution. Note that we really start with 1, 2, 3. That's k. Here we have our pk. We start somewhere here, and you see that this is a function in k. It's an exponential function in k, so it's a distribution which decays exponentially. And this distribution is called the geometric distribution. So waiting times follow a geometric distribution, and so waiting times decay exponentially. Because something's to power k, so this goes exponentially with k. And this is what I told you already in the continuous exponential distribution, that exponential distributions always have something to do with waiting times. And here in the simplest case we have a discrete binary variable. We wait until we have a success, and this has the geometric distribution. So now let's calculate the typical time we need to have success. So let's calculate averages. So how do we calculate the expected value of k? So now it's just a straightforward application. It might, if you're not used to this calculation, it's just straightforward application of our definitions. So we have infinite many, so this k can be infinite large. So we have an infinite sum here for the expectation value, and let me write down the sum first in terms. We always have this value p, which we can take out, and now take the coefficients in the sequence of the expectation value. So we have this 1 minus p to we start with k equal 1, so 1 minus 1 gives 0 times 1 plus 1 minus p to power 1 times 2, and so on and so forth. 1 minus p to power 2 times 3, and then we close the parentheses. And but of course we can write it also more formally. 1 minus p to k minus 1 times k, and k goes from 1 to infinity, because this is just the expectation value. But if you're not used to this sum formula, it helps to really express the sum, write all the terms down, and then you see sometimes the pattern that we do here more easily. So we always call this 1 minus p, we call this q. Let's do this here also, so that helps with the notation. So we have here a sum with p, and then we have q to k minus 1 times k, and k goes from k goes from 1 to infinity. And now we want to work out what is the value of this infinite series. And what we want to use, let me write this down here. Very often with these, you always try to get this to a geometric series. So that the sum of some q to power k, where k goes from 0 to infinite, this should be q here, is just 1 over 1 minus q, if q is smaller than 1. Oh, sorry. Let's write it to say it again. So like if you have a sum of q to power k, you sum over infinite many terms. This is 1 over 1 minus q if q is small enough. That's a geometric series. I assume that you all know this or had this once in math. I will not prove this. But the trick with such expressions here is now, can we rewrite this in such a way that we obtain the geometric series? And see, we're close. We have here k minus 1, we need k, and we have a k too much here. So now how can we, and we sum here from k equal 1, but we should actually sum from k equals 0. But you see, we could directly write the sum from 0, because if k equals 0, this doesn't change anything. So first we can change this here by k equals 0, we don't make a mistake. So and now let's see how can we rewrite this in order to go somewhere here. And it's always the same tricks that people do here. And one trick is, if you have such a series and you have something to power k times k, this is something like a derivative of something. So let's see if we can rewrite this. First, let's write this like p over q, and then we can write this as q to k times k, and the sum runs always now from k equals 0. So what did we do? This k minus 1, this term 1 minus 1, I didn't like here so much, so I just wrote here 1 over q, here I multiplied with q, and this is a bit more simple. And now how can we get rid of this k here? So keep this P over Q. And now in the sum we can see if we write this Q times D over dQ times Q to power K. So if we take the derivative, we would get K times Q to K minus 1. Then we multiply with Q again, and we get K times Q to power K. So in this way we have rewritten this term, and this factor K is gone. Now you see this these terms here do not depend on K. So this Q anyhow we can cancel. So we just have P times D over dQ. And then we have the sum Q to power K. K goes from 0 to infinity. And here suddenly we have found our geometric series. So we can plug this in. P D over dQ, and the geometric series is 1 over 1 minus Q. And now we need to take the derivative of 1 over 1 minus Q. So we have P, and then we have here 1 over 1 minus Q squared. This was just taking the derivative. And now remember 1 minus Q is P. And then we have here P over P squared is 1 over P. And this is the expectation value of the waiting time. So with this I showed you first how you can calculate such an expectation value in a more, let's say, a little bit more difficult example. And there is quite a number of tricks that are used again and again in these calculations. You try to change maybe the range of the variable that it runs. You try to, if you have something like k minus 1, we make something like this to get this to power k. And then we try to work with derivatives in order to get some coefficients here. And so we, here in particular, this operator Q times D over dQ is there a prominent thing. And then you just work it through and you can calculate the expectation value. Now in a very similar way, we could now calculate the variance, or the second moment. And when we calculate now the second moment, so we now we have here always powers k squared. This means we have to take this trick here, we have to apply this trick 2 times. So this gets a little bit more complicated, and you can use the same method to calculate the second moment. And here I would really ask you, stop the video, take your time, take paper and try to calculate the second moment. So what I will do, I will skip this because it's just straightforward calculation. Instead, we want now to see, can we do this with the generating function? And maybe it's the first time where the generating function already helps us, and things get a little bit more easy when we use the generating function. But since the video is too long, I make a stop. In the next video I will calculate the generating function for the waiting time and then calculate the moments. For the moment, thank you.